Hey guys, this is Mr. Bennett and this is Unit 16, video number 2. We're going to talk about reaction rates. And in fact, we are going to talk about things that we already know about reactions before we get into the new stuff. So here I have a reaction. We have hydrogen gas combining or reacting with oxygen gas to form water, and we also know that energy is released. So the first thing we know about this reaction is that the arrow in the middle shows us the flow of the reaction. In other words, it's going from reactants on this side, and we know that products are produced on the right. So in other words, the arrow points towards the products. Okay. Other things that we know this is a balanced equation. We can count up the number of hydrogens on the left. There are 4 atoms of hydrogen on the left, and there are 4 on the right. There are 2 atoms of oxygen on the left, and there are 2 on the right. So we know it's a balanced equation. We also know that these little guys here, these tell us the phase. So in other words, because these all have G's, that means that's a gas. We know that there are other phases like liquids, solids, and we know that if a substance is dissolved in water, we call that aqueous. So if it said AQ here, that would mean that was aqueous. And then the last thing we know is we know that, based on what's here, we know that this over here, this is energy. And because it's on the right side, meaning it's on the product side, we know that energy is exiting the reaction. So this is an exothermic reaction. Okay. There's one more thing that we could add to this. It's not in this particular reaction, but let's say that there was a substance up here written above the arrow. We'll call it substance X. We know that that would be called a catalyst because catalysts do not take part in the reaction. In other words, or at least they're not used up in the reaction. So they're not on the reactant side, and they're not made by the reaction, so they're not on the product side. They do participate in the reaction, though. So they get a special spot just above the arrow. Okay. The last thing I want to review about this reaction is the idea that there's an energy change throughout the course of the reaction. So in other words, the reactants have a certain amount of energy. The products have a certain amount of energy. But we know that over the course of the reaction, these guys react, we make products, and energy is given off or lost. So another way of thinking of that is, if this is energy going up this way, okay, and this is the reaction progress, okay, so now meaning from start to finish, we know that our reactants are up here in terms of energy, and we know that our products are down here. So over the course of the reaction, the reactants combine, forming the products, but energy is lost. So this right here, this 242 kilojoules, represents the difference in energy between the products and the reactants. So this would be like your 242 kilojoules that are given off here. Okay, so this is just an energy diagram showing how the energy changes throughout the reaction. Okay, so that's all reviewed. That's stuff that we know. Okay, now let's talk about the mechanics of a reaction, because this is where we're going to apply everything that we've learned this semester to reactions and kind of grow or expand our knowledge of how reactions work. So to understand the mechanics of a reaction, you got to think back to one of the concepts that we've talked about a lot this semester, and that is that in order for reactants to react, they must collide. So we've talked a lot about collisions this semester, whether we're talking about the creation of pressure, we've talked about things dissolving, so the solvent particles have to collide with the solute in order to break it up or dissolve it. So collision is really big for this semester, and that leads us to the collision theory. The collision theory says that reactant particles react to form products if they collide with enough energy. So there's really 2 particular requirements in order for products to form. And that is, first of all, they have to collide correctly. So in other words, they have to collide with the correct 3-dimensional arrangement or orientation, and we call this the activation complex. So activation complex. In other words, you could think of it as 2 reactants approach each other, they're going to interact, or as they collide, they're going to interact to form the product. But if they don't collide in the correct way, they're just going to bounce off and nothing will happen. The equivalent kind of analogy would be a key in a lock. So if you throw a key at a lock, or you put a key towards a lock, right, and it doesn't hit the actual keyhole, then even though the key came in contact with the lock, it's not going to unlock unless you put it in the keyhole the correct way. So you have to form the right three-dimensional arrangement between the key and the lock to actually get the lock to unlock. Okay? Same thing with chemicals. They can collide, but that doesn't mean you're going to get products. They have to collide in just the right way, just the right three-dimensional arrangement for them to interact. You also have to have enough energy. Okay? And we call this the energy of activation. Okay? So the idea here is you have to have the payment, the energy required to not only get them in a three-dimensional arrangement, but also to break or kind of adjust any chemical bonds that might be present. So we can think of the energy of activation over here as you have your reactants that start the reaction. Okay, you have to, first of all, they have to collide, and then once they collide, a certain amount of energy has to be put in. So you have to input. Notice this is potential energy on the left. So as we go up here, we're adding energy, and then once you've added that energy, you get your products. Okay, and so we would call this little section here, from the top of this hill to the energy that the reactants began with, this we would call the energy of activation. Okay, now notice that the products are all the way down here. Well, they have less energy than the reactants right now. So based on our graph that we just saw earlier, we would say that this is an exothermic reaction, because from reactant to product we lost energy. Okay, so we had our reactants, they collided, the correct amount of activation energy was provided, and then the reaction occurred, energy was given off or released, and we formed our products. Okay, notice that if we had paid the activation energy, but let's say the products formed right here, right? So if the products formed right here instead of down here, the products would have more energy than the reactants, and we would call this an endothermic reaction because they actually absorbed energy. Okay? But the overall idea here is there are two requirements. First of all, they have to collide with the correct arrangement. We call that the activation complex. And then they have to collide with enough energy. That's the energy of activation. Okay? Now let's talk about how we measure reaction rates. So we know what needs to happen for a reaction to occur, but how do we figure out how fast the reaction is occurring? Well, there's two ways you can determine the rate of a reaction. Essentially, as the reaction occurs, reactants are used up. Right? So in other words, their concentration decreases. So you can measure how fast the concentration of reactants is decreasing or disappearing. And then on the flip side, products are made. So that means that their concentration increases. And so if you want to measure the rate of a reaction, you could measure how fast the reactants are being used up, or the concentration is decreasing, but you could also measure the products. You could see how fast are they being made, how fast is their concentration increasing. Both of those ways, both of those methods could be used to measure how fast a reaction is actually happening. Okay, so let's say that this rate, you measure it, but you want to increase it. So let's say you really, really want products and you really want them fast. How can we change reaction rates? Well, so this actually goes back to what we were talking about earlier in terms of collisions, and that is that anything that increases the collision of reactants will increases the reaction rate. So if you can create more collisions, that means that you have more opportunities for the reactants to collide and hopefully form an activation complex, and if they collide with enough energy, you'll get a reaction. That doesn't mean that every collision reacts or creates a reaction, but it does mean that every collision is an opportunity for the right activation complex and activation energy to show up. So the more collisions you have, the more likely or the more of a chance that both those things will happen. So how can we increase the number of collisions? The first thing we can do is we can increase the concentration of reactants. So in other words, if you put more reactants in the container, that means more reactants are bouncing around, which means there's more likely that they're going to run into each other. Okay? The second way we can do this is we can increase the temperature. So along the same ideas, if instead of adding more reactants, if you increase the temperature, you're going to increase the kinetic energy, which means that the reactants are going to be moving around faster and with more energy. If they're moving around faster, that means more collisions, and they have more energy now, so it's more likely that they'll have the energy necessary to pay the activation energy. So you just are waiting for the right collision to occur with the right activation complex, the right arrangement or 3D orientation, and then you have the kinetic energy because you've raised the temperature. Okay. The third way you could do it is you could increase the pressure. Okay. Now, if you think about this, the way we increase the pressure is we decrease the volume. Okay. We essentially put force that is pushing the reactants closer together, and if they're being pushed closer together, that means that they have less space, less free space to move around, which means that they're going to collide more often. Again, creating more collisions. If you have more collisions, you have more opportunities for that activation complex to form, and then hopefully it has enough activation energy to create the products. Now the fourth and final way that you can change reaction rates is something we talked about earlier, and that would be to add a catalyst. Okay, so what is a catalyst? A catalyst is a substance that brings reactants together in the proper activation complex. So just like how increasing the temperature was a way of increasing the kinetic energy, right? And in turn, that helped pay the activation energy. With catalysts, instead of trying to put the activation energy together, we are trying to put the right activation complex together. So you could think of it as, if this is my catalyst, right? So here's my catalyst, and then I have my two reactants, right? My reactants can fit right in here, and they're right next to each other. So the catalyst is going to kind of collect our reactants, put them right next to each other so they're in the right activation complex or three-dimensional arrangement right next to each other so that the reaction can occur. Okay? You're no longer waiting for the right collision from the right angle to occur. The catalyst actually brings them together in the right orientation. So going back to that key in the lock idea, it's essentially your hand which is bringing the key towards the lock, helping it, guiding it into that keyhole, bringing the two together in the right or proper three-dimensional arrangement. Okay. Now the unique thing about a catalyst is that they are not used up. In other words, they are reusable. Okay, and overall they do lower the activation energy because since they're right next to each other and they're being held together really close, the reactants don't need quite as much activation energy to create the reaction. So not only do they help the activation complex form, but catalysts also lower the activation energy. So if we were to go back to that graph that we saw earlier where we have the reactants and we have the products, right? We pay the activation energy to get, whoops, that was supposed to be a P for product. Okay, so we pay our activation energy to get our products. If we add a catalyst, draw a little red line here, we don't need as much energy of activation. So we need less energy of activation, but we get the same product. Okay, so that is essentially video number 1. Make sure you complete your whisk, and we'll see you tomorrow.